The next concept that we're going to look at are buffered solutions. And buffered solutions use this concept of the common ion effect, but enable us to consider how solutions can actually minimize the effect of adding a strong base or a strong acid by limiting how much the pH is changed of their solutions. So buffers specifically are solutions that contain a weak conjugate acid-base pair, and they can resist drastic changes in pH when small amounts of strong acid or base are added. Now, they resist change because if, for example, a strong base is added, so hydroxide ion is added, the weak acid, so in this case HF, is able to react with the hydroxide ion in order to produce water and fluoride ion. If you just had hydroxide in solution and it wasn't consumed, then that would severely increase the pH of the solution. But since we can increase the concentration of the fluoride ion, which is a weak base, that limits how much the pH is going to change. In contrast, if I add a strong acid, H+, then the fluoride ion is going to act as a weak base with that strong acid, and it's going to produce hydrofluoric acid, which is a weak acid. Again, it causes the pH to decrease, but only slightly, not as much as if hydrogen ions were allowed to exist in solution by themselves. And the way that we prepare them is by mixing a weak acid or a weak base with a salt of that acid or base. So for example, NH3 would be mixed with NH4Cl, ammonium chloride, because ammonium, that ion, is its conjugate base. So this should bring to mind the concept of the common ion effect, and that's exactly what it is, having a strong electrolyte in solution in conjunction with its either weak base or weak acid. In this problem, it asks you to calculate the pH of a buffer that's composed of 0.12 molar benzoic acid and 0.20 molar sodium benzoate. So I'm actually going to show how to do this two different ways. The first one I'm going to show you is using ice charts in order to determine the pH. And then I'm also going to show you the fact that you can actually use the Henderson-Hasselbalch equation. So for this reaction, I'm going to show the dissociation of benzoic acid. The formula for benzoic acid is the following. And this is going to dissociate, it's a weak acid, it's going to dissociate into hydrogen ion plus C7H5O2 minus. Okay. The only information that's not given to you in this problem is the acid dissociation constant, which is 6.3 times 10 to the negative fifth. Okay, so let's solve for the pH of this buffer. I'm going to create my ice chart. I know that the initial concentration for benzoic acid is 0.12 molar. I know that the initial concentration for the benzoate is 0.20 molar. I know the initial concentration of hydrogen ions is 0. So I'm going to lose X, gain X, and gain X for this reaction. So my equilibrium concentrations will be the following. Now I can actually plug this in for my equilibrium expression. So my Ka, which is 6.3 times 10 to the negative fifth, that equals X, my concentration of hydrogen ions, times 0.20 plus X, divided by the concentration of my benzoic acid, which is 0.12 minus X. Again, remember, I'm assuming that this change in X and this change in X are not significant, and therefore when I solve this, I end up with 7.56 times 10 to the negative 6 once I cross multiply 0.12 by 6.3 times 10 to the negative fifth. I'm going to set that equal to 0.20 times X. Therefore, when I solve for X, I get 3.78 times 10 to the negative fifth molar. Now all I need to do is calculate my pH. So my pH equals the negative log of that value because that's my concentration of H+. And so when I calculate that, I end up getting 4.42 for my pH. Now the other way of doing this, I agree that I'm not at equilibrium with this problem, but since we ignore the change in X, so the change in concentration for these two, I can assume that my initial concentration for my acid and its conjugate base are going to be the same as the equilibrium. So the equilibrium concentration and the initial concentration are the same. So I can actually just use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is pH equals pKa plus the log of your concentration of your base divided by the concentration of your acid. So my pKa, the negative log of 6.3 times 10 to the negative fifth, is 4.2 plus, 4.2 plus the log of my concentration of my base divided by my concentration of my acid, and that ratio is actually 1.67. And so when I solve for the pH, I end up with 4.42, which is exactly what I got there. So you can do it either way. I personally prefer to use ice charts. However, obviously the Henderson-Hasselbalch equation is much quicker to solve. So in order to calculate the pH of a buffer that has had an acid or a base added to it, what you need to do, let's say for example, a strong acid is added to a buffer. You need to look at the reaction that occurs, so you can see X minus, which is your weak base, reacting with the strong acid to produce HX. You need to calculate the new values for the concentration of your acid, HX, and your weak base. With those new values, you can calculate the pH by using either ice charts or the Henderson-Hasselbalch equation, and I'll show you an example of that in just 1 second. If a strong base is added, then that's going to react with your weak acid, and then you again will need to calculate your new values for your weak acid and your weak base, and then again use ice charts or Henderson-Hasselbalch equation to calculate the new pH. In this problem, you have a buffer that's created with acetic acid and sodium acetate, and what it's asking you is to determine the pH of the buffer once you add a strong acid. So before you get started with this problem showing the dissociation of the weak acid, what you should do is figure out, okay, what is hydrochloric acid going to react with, and figuring out how that affects the concentration of your acetic acid and your acetate ion. And so what you should realize is, since this is an acid, it's actually going to react with the acetate ion, which is C2H3O2, and so it's going to react with your strong acid, and it's going to produce acetic acid. So we need to determine stoichiometrically how this affects our concentration of our weak acid and our weak base. So specifically, I know that I start off with 0.3 moles of my acetate ion, and I have 0.020 moles of my strong acid, and then I have 0.300 moles of my weak acid. So in order for all of the hydrogen ion to be consumed, which it must in order for the buffer to be effective, you must use all of this up, which means it's going to consume that amount of your acetate ion, which means it's going to add that much to your acid. Keep in mind, I am remembering the stoichiometry relationships, however, there are no coefficients, and therefore it's just all X. So for here, my new concentration of my acetate ion is going to be 0.280 moles. I have no strong acid left, that's the point, and then I have 0.320 moles of my weak acid. Now I can determine the concentration of these guys. So I'm going to divide both of them by the volume of the solution, which was 1.00 liters. So I know that the concentration of my acetate ion is just going to be 0.280 molar after the strong acid was added, and then the concentration of my acetic acid is going to be 0.320 molar. And now I can actually determine the pH of my buffer. So there are two ways that I can solve this problem. I can use an ice chart, or I can simply use the Henderson-Hasselbalch equation. Remember, the Henderson-Hasselbalch equation is pH equals pKa plus the log of the concentration of the base divided by the concentration of the acid. Now there's one key important point that you need to note. What you should notice is the fact that I'm not given my acid dissociation constant, and so as a result what I'm going to have to do is make an assumption, and that assumption is the following. Since buffers are the most effective when the concentration of their conjugate acid and base are the same, before this entire reaction occurred, I should assume that the log of this entire thing, so the log is going to be the log of 1, assuming that it's the most effective buffer. Therefore, this value is 0 because the log of 1 is 0. Therefore, my pH equals my pKa. And so for here, my pKa will simply be the pH of the buffered solution. So the pKa is going to be 4.74. Then I'm going to add to that the log of the concentration of my base over my acid. So that's going to be 0.280 divided by 0.320, and what I end up getting here is 4.68. If you did this same problem, except you actually used an ice chart, you would get the same value. Now, the second part of this question asks us to determine the pH of a solution if that amount of HCl were added to pure water. Well, in this case, you just have HCl, and so it's going to produce hydrogen ions and chloride ions. Since the concentration is 0.02, I know that the concentration of H plus that's produced is also going to be 0.020 because this is a strong acid, and since it was in 1 liter of water, it's going to be 0.020 molar. Therefore, when I find the pH of this, I find that it's 1.70. So notice how important a buffer is, or how effective it is at reducing the amount that a strong acid can change the pH, because the pH was only changed from 4.74 to 4.68, while here the pH was changed from 7 of pure water all the way down to 1.70. So that shows you the value of a buffer in minimizing the effect a strong acid, or in other examples, a strong base will have in changing the pH of that substance.